Yeah, so as the name suggests, I'm going to be talking about a specific use case of collaborative filtering in which basically the users don't specific ratings on the data. But more generally, this talk is about making sure that your data is dictating your model and that your evaluation is dictated by your use case. So just in case you all are sleepy after lunch, I'll tell you what I'm going to say before you have to listen to the whole talk. So I'm going to start with a general overview about recommendation systems, how they're used and built. Then I'll go into a bit of detail about our specific use case. So we ended up deciding to use AWS and Spark for medium-sized data at scale, and I'll tell you more about what I mean by that. And it's in order to build a recommender system that was based purely on purchase data. So there's no feedback from the users. I'm going to talk about two different models that we evaluated for this. So item-based nearest neighbors and matrix factorization. And I'm going to talk a lot about evaluation of those models and how you select the best model when you lack explicit feedback. And then finally, I'm going to touch briefly on the importance of making sure your presentation is right. So incorporating business logic, having good cold start solutions to really get the most out of your system. So all of you have seen recommender systems. If you go on Netflix, if you go on Amazon, as soon as you start clicking on things, you're getting a lot of basically recommendations. You're not using search. You're saying, OK, we recommend that you look at these things because you're looking at this particular item. And most of the people in this room are likely familiar with the Netflix prize, in which Netflix offered $1 million to the team that could improve their recommendations algorithm by 10%. And this is basically just an example of a company putting their money behind just how important having a good recommender system was for their business. So there are a number of ways that these recommender systems can be built. So there's collaborative filtering models, which is sort of taking the wisdom of the crowd and using that to produce recommendations. There's also content-based approaches. So if you know something about your users, you know something about your items, you can take that information to try and predict which users and items will be a good match. And of course, you can combine these techniques to get often enhanced results. What I'm going to talk about today is actually collaborative filtering techniques. Within collaborative filtering, there's neighborhood-based models or memory-based models, where basically you look at users or items and try and predict similarity to the item, what the user has done to the item that you're going to be recommending. There's also model-based approaches such as matrix factorization, which try and come up with underlying features that describe users and items. And then again, you can combine these techniques. So a bit more about what we're trying to do. So Salesforce has data from a lot of different companies. And this data is individual to the companies. It doesn't touch other companies. It doesn't mix. But we want to be able to produce recommendations for each of these companies. So take the data from the company, put it through a collaborative filtering algorithm, recommend the top K products. Now, individual data for the companies may not be that big. But if you take all the companies combined, it really does end up being a big data problem. And so you have to deal with that scale. And as you can tell by the venue, we chose to use Spark to deal with this. So basically, Spark's sitting on top of AWS. And we chose this for a number of reasons, despite that the fact that it required sort of a new terms of service for users, which is basically that we needed something that we could scale from a few customers to handling many customers very rapidly. And we didn't want to reinvent the wheel. So Spark MLlib has pretty good libraries, and it's getting drastically better with every release. In fact, it's really impressive how much it improves every single release. And so we wanted to bootstrap off of that. So when you have data that's coming from different companies, the data is fairly heterogeneous. But one of the things that we could definitely count on being there was if a user bought something. So this is consistent across companies. This makes it easy to build a product that will apply to multiple companies. And from that purchase information, we want to recommend a list of items, the top K items. But purchase information is somewhat different because if this little bubble guy here bought a picture, he bought a book, and he bought this movie, but he didn't buy the game controller, we don't know why he didn't buy the game controller. It might be because he didn't like it. It might be because he didn't see it. And those are two very different things when you're trying to build a model, but we really have no way of distinguishing them. So in order to deal with this kind of data, you have to choose the right model. And in choosing the right model, again, you have to start with your data. So our data doesn't have ratings. It ends up looking something like this. So you have a user ID, a product ID, and maybe a date of purchased. And this type of data is again, implicit, unary, binary, whatever you want to call it. But fortunately, there are a number of candidates of models that are good for this. So item-based nearest neighbors is one. Matrix factorization of implicit data is another. And you could probably add a few more to this list, but I'm going to argue that these would be your top contenders, and go ahead and go into some depth about these two types of models. And then finally, just again to point out, evaluating the models is really the key to getting good results. So a bit about item-based nearest neighbors. The nice thing about it is that it's very simple to compute and explain, and it tends to be more scalable than user-based and more stable. So items aren't changing as quickly as user preferences. And the way you go about computing item-based neighborhoods is essentially you want to compute a distance metric between all items. In this case, the distance metric is not for sort of the underlying similarity of items, but a distance for likelihood of being purchased together. And so the way you can do this is with a Jacquard similarity. Again, there are other metrics you could use, but this one is very nice for unary data. And so essentially what you can say is if you have all the users who purchased item A, all the users who purchased item B, take the intersect of users who purchased both, and divide that by the union of users who purchased either. And that will give you your similarity. Once you have that similarity, you can take the top K most similar items and use that as your similar neighborhood. And then you can use that similar neighborhood to make your recommendation. So essentially, if you're trying to estimate a rating for user on a particular item, what you do is sum across the set of similar items the similarity of your set to the item you're trying to rate, multiplied by the rating the user gave the similar item, and then divide that by the total sum of similarities. And this will give you your estimated rating. And just a quick example of how this ends up working. So say a user purchased a hat. What you might end up recommending to them would be a coat, scarf, and gloves, but you wouldn't recommend jeans or a table. And while this wasn't in Spark when we were implementing it, it might be in the latest release. I haven't even looked. But it's really simple to compute. So essentially, almost the entire model fits on this one screen. What you can see is you can compute the Jacquard similarity simply using sets as a cheat. You can compute the map of similar items by basically passing in your training data, which would be an RDD of ratings, so user, item, and rating. Basically group the data by product, convert your users into your set, do a Cartesian self-join on the data, and then compute the similarity between the user sets for the two bits of data and keep your K most similar items. And this is pretty much all you need for the model. There's a couple of other things. So you need the actual computation of the rating and a list of items that a user purchased. But it's right there. It's not hard to do, and it works pretty well. So the other type of model is this matrix factorization. And it's matrix factorization specifically for implicit data. So in general, matrix factorization is just a way of finding a reduced dimensionality representation for users and products. And so the way that works is you get your matrix where you have users in rows, products in columns, and it's filled in with basically, in this case, zeros or ones, depending on whether or not the user bought the products. This is n by m, and what you're trying to do is find basically the features that represent users and the features that represent products, such that with these reduced matrices, you can multiply them together and recreate the original matrix. And the nice thing about this is that it's parallelizable with alternating least squares, which came out of the Netflix challenge. And it can be applied to implicit data, and that application is already in Spark MLlib. So it ends up being quite easy to use. You can just import it and say train, which works out very nicely. And so the important part of this in using this with implicit data is in this equation here. So if you don't like math, you can read the quote from the MLlib comments. If you do, then essentially the important part of this equation is that for matrix factorization, what you're trying to do is minimize this. This is the equation for implicit matrix factorization. So if you look in the first part before the plus sign, what you can see is that for standard matrix factorization within the parentheses there, you're trying to minimize the difference between a user's preference for a particular item and your estimate, so your user feature vector multiplied by your item feature vector. You're trying to minimize the sum square error of that. And the addition with implicit data is that you're actually you're adding in a confidence for that preference. So the preference is set to 0 or 1, depending on whether or not the user purchased it. And then you have some confidence level associated with how much do you think they actually like the item. And this is the alpha parameter that you set with your implicit training. And then the second part of that equation is just the regularization parameter. So essentially, your lambda, you're putting a penalty on how large your feature vectors are. So those are the two models that we want to test and evaluate. But then again, there comes another issue, which is simply the lack of negative data in your data set. So if you follow the standard procedure where you basically take your data, you divide it up into training, validation, and test sets, or training, which is then treated with k-fold cross-validation, you have some issue when you try and do your validation, because if you're looking at something where basically everything you're validating on is a 1, the best fit to that is basically a model that says the user will like everything or will purchase everything. And that's not actually what you want to do with a recommender system. So there's a number of ways that you can deal with this. One is to sort of generate negative values. And you can do this by randomly assigning things that weren't purchased as zeros or negatives. And the reason that this works is because if you consider the space of all possible items and the space of items that the user actually would like, the space of items that the user would like is much smaller, relatively speaking. And so when you randomly select something, the chances of you getting something in that space of actually good items is small. So it's a hack, but it works, and it gives you some usable metrics. And the other thing that you can do is sort of focus on your top K recommendations. So if you're going to be presenting users with a list, go ahead and generate that list, and then measure recall on the holdout set if it's a small list. If it's a long list, then you want to look at a rank metric, so mean reciprocal rank or normalized discounted cumulative gain for your holdout set. And then again, remember that offline testing is not perfect, so you need to follow this up with testing in the wild and make sure that really what you're building works when you put it into production. So one of the reasons that you need good evaluation is for hyperparameter tuning. So if you look just at the list of parameters that you pass in to alternating least squares fitting for matrix factorization, you can rapidly end up doing hundreds of model fits. And this is time and resource intensive. But the correct hyperparameters really do depend exactly on your data. And so you have to do this across the data sets. And it really improves your performance. However, the nice thing about Spark is that if you're clever about it, you can parallelize this and save yourself a lot of time, and in particular if you have flexible resources. But in order to do this right, you need the right evaluation metric. So the first thing is just a quick point about what not to use. So root mean square error is the most commonly used evaluation metric for machine learning. But if you've got unary data, it's not really going to tell you very much. So what I've plotted here is the root mean square error fit for 3 different model types. So matrix factorization for implicit data, explicit data, and an item-based nearest neighbors. And on the bottom, what I've plotted is the number of times the model correctly predicted something from my holdout set, so true positive rate. And if you imagine that there's 25,000 actual true positives in my holdout set, what you can see is that the root mean square error is not even correlated with that value. So it's really not going to help you with hyperparameter tuning if that's what you're doing your final evaluation on. So what can you use? So in the instance where you're generating sort of random negatives, one thing that you can do is precision and recall, or the F1 harmonic of them. So essentially, you look at your holdout set, and you have some true positives that are generated, and you can look at essentially what percentage of the total true positives appeared in your data set. And then precision is the flip side of that. So of the things that the model predicted would be liked, what percentage of them were actually in your holdout. And this is nice, so you can see it's sort of actually smoothly varying. It allows you to look at trade-offs between the models. So you can see here that item-based nearest neighbors is a little bit better on precision. ALS implicit tends to do a little bit better on recall. And explicit varies wildly and has a tendency to predict nothing. You can see the tiny little yellow dot at 0, 0 there. So the other thing you can do is, again, going back to this list of top Ks. But one thing to keep in mind is that if you're doing top K and your list is very long, you're sort of increasing the chance that you will predict your holdout set. So it's a gameable metric. And if you're doing a really long list and something that the user has to flip through multiple pages to see all of it, then you really want to use a ranking metric. If it's a short list, they can see everything in one slide, then maybe recall is the best bet. But again, it's actually closer to what you're doing. Unfortunately, one of the things you want to do with a recommender system is predict new items. And you don't have any way of knowing what the other K minus the held out set are, or how good they are. And for that kind of evaluation, you really have to go to the wild. But this at least gives you a starting point. So which should you use for your evaluation? As you can see, these 2 metrics are correlated. So I have recall plotted for generated zeros and recall on a top K. You can see that they are related for different models, though it's not perfect. And so the answer to which one you should use really depends on what your use case is. So if you are going to be showing users a list, use a list-based metric. If you want to predict how much users are going to like something, then generate zeros. And also, you can sort of keep in mind that top K can be more computationally expensive to generate if timing is a constraint. But if that's your final use case, you're going to have to deal with that complexity at some point anyways. So just a word about how this evaluation works across data sets and how these models perform across data sets. So what I've plotted here is essentially the best fit for the 3 different models. So item-based nearest neighbors, ALS for implicit data, and explicit data. And the data varies mostly in sort of the relationship between how many products a user bought. So in this first set, what happened was there were a lot of products which were purchased by very few users. And you can see that item-based nearest neighbors worked better for that. On the other hand, on these second 2 data sets, users purchased a lot more items. And alternating least squares work better. So it really is data set dependent which model is going to perform best. And you need to explore a number of different models in order to get the best answers. But it is possible with the right evaluation to get good answers. So a quick word about the processing time for these models. So as you can see from these 2 graphs, sort of alternating least squares, if you look at the axis, took about twice as long to fit. but both can end up taking a while if your data set is large enough. How the variation within model fits, again, dependent sort of on the structure of your data. So how many items, how many users are really the big dictators, and not the sort of overall volume of ratings that you're evaluating on. But fortunately, if the time to fit is a concern, both item-based nearest neighbors and matrix factorization have sort of cheats that you can use. So you can do pseudo-updating to get real-time-ish recommendations. So take into account the items that a user purchased since the last time you trained your model and feed that in to make your recommendations. And this can save you time in refitting. And the other thing to keep in mind is the serving time. So if you're going to be making a lot of calls for lists, then maybe you want to do offline jobs and serve to a key value store to make that latency faster. So even if you've gone through the evaluation and selected a model that works the best for your particular data set, you still need to consider the cold start problem, right? So what do you do when there's a new user, when there's a new item? And in particular, for data sets where there are a lot of sparse items or users only come in and purchase one or two things, making sure that you have the right recommendations for the cold start can give you a huge lift, so better than 20% for some data sets. But the other thing to consider is really sort of the business logic around your model. So if new items are very important, you want to present a way for companies and particularly the people in charge of what users are seeing to really lift those items up. And so basically what this is saying is on top of your model, you want to have a layer of business logic that's letting additional concerns and constraints be put in. You don't want to let your model sort of run free and recommend things. And the other way to do this is if you have metadata that you can combine, basically taking that metadata to try and make more specific cold start recommendations. So if you know something about the user, you can sort of cluster them or use some content-based recommendations to combine with your collaborative filtering techniques. All right, so sort of walked you through a lot of stuff. In case you actually took that nap, what were my main points? So I think the big one here is the tools are out there, and don't spend time reinventing what you don't have to. MLlib is actually a really nice library, and it's getting better so rapidly. And so if you can use that, if you can leverage that, it's going to save you a lot of time. The other point is that, given sort of the overall nature of machine learning libraries, so they're big, they're iterative, if you have something that doesn't have to write to disk between every iteration, it runs a lot faster. So Spark is really great for that. And I think the big lesson from all of this is just really, before you start applying your favorite model, think about what your use case is, and think about what your data looks like. So data should dictate your model, and your goals need to dictate your evaluation. So make sure that your evaluation is as close to your final goals as possible to get the best you can offline, and then really make sure that you follow it up with online evaluation. And then final point is that the details of presentation are really important. So the best algorithm can't overcome just a terrible UI. So really it needs to be presented to users well and in a way that they'll understand. All right, thank you.
You mentioned what the cold start process was like for the system as a whole. Mm-hmm. Can you talk a little bit about what's the process when new products come online?
So for new products, it really depends on the business. So it may be, for some businesses, the new product might not be as important for it, and then essentially you can just sort of leave it to other mechanisms to expose that product and get some purchases. If it's really important for new products to be incorporated in the recommendations, so it's a really important product, then that's where sort of the business layer comes online, and you basically say, I'm going to put this into recommendations no matter what. So.
Hi, I noticed that in the dataset C, which you mentioned, there was a significant like time difference when you used matrix factorization.
Mm-hmm.
Is it because the alternating least square took quite some time to converge, or was there like significant difference in terms of data dimensions?
No, so those were all run with the same number of iterations. It was actually a difference in that data set had many more different users and products.
Right, so it was much
so
more
the matrix
sparse.
was much bigger. Yeah.
Hi. So let's just say if you have seasonal products, and if you have certain users who only, you see those users only in your system when, let's just say in winters or whatever. So do your recommendations change based on time? Let's just say if I see a user in January and don't see that particular user until October or something, do your recommendations change over time, or?
Yeah, so if you're retraining your model periodically, then you can capture some of those changes. I think if it's really seasonal, that's tough to capture with this type of model. There are recommendation models that can do that, but they're a lot trickier to implement. So.
Thanks.
All right. Thank you.